Here's another way to express how these things work. On the left-hand side, you have a cold sample, not much movement, low temperature. On the other hand, on the right, then you have a high movement and high temperature. And it's totally possible to change the energy of the sample without changing the phase. So for example, if you take liquid water at 20 degrees Celsius, you can heat it to liquid water at 40 degrees Celsius, and it's still liquid water. You could also take liquid water at 20 degrees Celsius and cool it to 10 degrees Celsius, and it would still be liquid water. So if you have a heat change, but no change in state, you're not going from a liquid to a solid or a liquid to a gas or any combination like that, then you can use this equation right here, which is going to be very helpful to us. And it's Q equals mc delta T. Now, Q is the heat transferred, and it can be Q sub P delta H, or it could be just regular Q. It doesn't really matter. But for us right now, Q is a measure of unit in heat, which is joules, all right? So the value of Q is going to be so many joules. And we have here an M, a mass, which is grams. There's a delta T, and that's the change in temperature. We'll talk more about that in a little bit. And finally, then there's the specific heat capacity, C. And every substance has its own heat capacity. So water, liquid water, has its specific heat capacity. Ethanol, drinking alcohol, has a different heat capacity. And that would be different than, say, solid sodium chloride, or even solid water, which is ice. Every compound in every phase has its own specific heat capacity. So Q equals mc delta T is the first important equation from this section, and it's how to figure out the heat transferred with no phase change. Now, phase just means you're not turning it from a solid into a liquid or a gas into a liquid. It's the same phase, just a liquid, just a solid, just a gas, something like that. And again, Q is the heat, and Q, as we're going to see, can be lost or gained, all right? So if the energy is lost, then that would be a negative Q, exothermic. On the other hand, you can have a positive Q where heat is gained, endothermic. M is the mass. It's usually in grams. C is called the heat capacity, and every substance has one of these. Water, for example, is 4.184. Bet you heard that number before if you were paying attention, but anyway, that's the value for liquid water. Most of the metals have heat capacities less than 1. Now, delta T. Delta is a symbol that's used in science. Delta always means final minus initial. So because this is a delta T, that's going to be the final temperature minus the initial temperature. So if your liquid water at 20 degrees Celsius was heated to liquid water at 30 degrees Celsius, delta T would be 30 minus 20, final temperature minus initial temperature. Delta T can be in Kelvin or degrees Celsius. The delta T for measurement is the same in Kelvin and Celsius, which is really cool. And then finally, Q, if it's positive, that's endothermic. Energy is flowing into the system, if you will, from the surroundings. On the other hand, if you have Q of negative, heat's flowing out from the system to the surroundings, and that's going to be an exothermic reaction. Every substance, like I said, has its own heat capacity, and every phase has its own heat capacity. We're going to use water, liquid water, so much that I would sure like you to memorize that number, 4.184. That's 4.184 joules per gram Kelvin. Now, you can use Kelvin. You could also use degrees Celsius. So you could also go 4.184 joules per gram degrees Celsius. But the heat capacity is nothing more than the joules required to raise 1 gram of an object by 1 degree Celsius or 1 Kelvin. So for example, in the table down there, it takes 0.84 joules to raise 1 gram of glass by 1 Kelvin. It takes 2.39 joules to raise 1 gram of a compound called ethylene glycol by 1 Kelvin. So every compound has a different value. Water is one of the higher values for heat capacity, and it's one of the things that makes water kind of special, and we'll talk about that later. Here's an example of how this process works. Let's say you have 25 grams, 25.0 grams of aluminum, and it's cooling from 310 Celsius to 37 degrees Celsius. The question is, how many joules of heat energy are lost by the aluminum? Now, Q equals mc delta T is what we're going to use to calculate it. If it's asking for joules, that means we're going to solve for Q, all right? And you will need a heat capacity. And I promise to give you heat capacities for everything but liquid water. I really want you to know liquid water. So know it / memorize it / put in your calculator, whatever you need to do. Aluminum is not liquid water. Aluminum is 0.902 joules per gram Kelvin. Remember, this little part right here means per. So it's like joules on the top, and in the bottom you would have grams and Kelvin. That's what that means. Don't be intimidated by it. It's going to pop up. So it would take 0.902 joules to raise 1 gram of aluminum by 1 Kelvin. Okay? These problems are kind of what I call plug and chug. You just put the different values in. Again, Q equals mc delta T. Specific heat is the C. And delta T again, final minus initial. Now, this aluminum is cooling. So it started out hot and it ended up cold. All right. Delta T can be in Celsius or Kelvin. It's totally up to you. So lazy chemist, me, all right, is going to just use Celsius because those are the values I got. There's nothing wrong with converting it to Kelvin first, but we'll talk about that. So Q equals mc delta T. Here's M, the mass, 25 grams. Here's C, the specific heat, which I gave to you. And then delta T, final minus initial. So 37 minus 310. Notice the dot there. So this number comes out to be negative 6,160 joules. The Q is a negative number, so that means it's exothermic. Heat is being given off as the aluminum cools down. That heat has to go somewhere. It's being released into the surroundings. The system, aluminum, is giving off the energy, no problem. Now, let's talk about the Kelvin thing real fast. The units for heat capacity, like this one, are often Kelvin. But if you add 273 to both of those numbers, all right, so 310 plus 273 and 37 plus 273, well, I don't even know what those numbers are, but the same thing's going to happen. You're going to get the same delta value if you add them up or not. It really doesn't matter for delta T if you use Celsius or Kelvin. Don't you dare use Fahrenheit on me. First of all, it's lame in terms of science, but second of all, you can't do the delta T trick when it comes to Fahrenheit. It only works with Celsius and Fahrenheit. A lot of times in science, like I said, people will measure Celsius temperatures in the lab and they'll use Kelvin temperatures for calculations. So the calculations part, which is what we're doing here, that's why it lists it as Kelvin. But there's nothing wrong with using it as Celsius, and I do recommend that you do that. The negative Q just means that heat's being transferred out of the aluminum. It's exothermic. The energy of the system has gone down, if you will. The energy is released. The energy would feel hot if you measured the container around the aluminum, something like that. And also, this is important, delta T can be Celsius or Kelvin. The difference in the temperatures will be the same. And try it, all right? Go 37 plus 273, whatever that is, minus 310 plus 273, and I guarantee it's going to be the same number. You can use Celsius or Kelvin. You are good to go. Here's a problem. 100 joules of heat energy is transferred to 5 grams of copper, initially at 20 degrees Celsius, and the final temperature is 71.9. Determine the specific heat capacity of the copper. All right, cool, no problem. So this is an mc delta T kind of problem as well. All right, and in this problem, you have the Q, which is 100. You have the mass, which is 5 grams. You have the temperature, final temperature minus initial temperature. So the only thing you're missing is the C value. And again, you need to know 4.184. That's the liquid heat capacity of water. I would give you heat capacities if they were needed, but in this one, you can actually calculate it for yourself. So throwing all those numbers into Q equals MC delta T, you're going to end up with 0.385. So 100 joules equals 5.0 grams times the heat capacity C, which we don't know initially, times delta T. And yes, I'm using Celsius. Lazy chemists of the world unite. We solve for C. C equals 100 joules divided by 5 grams times parentheses, and make sure you put the parentheses in, 71.9 minus 20. If you got 0.385, you are good to go. Heat capacities are always positive numbers. So in case you ever do get a negative heat capacity, just make it positive, because a negative heat capacity would imply that as you add energy, you would lose, the temperature would go down, and that just doesn't happen. So heat capacities must be positive. Here's another example. A piece of iron, 77.8 degrees Celsius, is placed in 244 grams of water at 18.8 degrees Celsius. What's the final temperature of the mixture? Now let's visualize here what's going on. We have a hot piece of iron and we're placing it in cold water. 77.8 is bigger than 18.8. So the hot and the cold are going to come together, and we're going to end up at some warm temperature for both the water and the iron, and that temperature will be somewhere between 77.8 and 18.8. And our goal is to solve for what that final temperature is. And it's not too hard. Now, conservation of energy says you can't create or destroy anything. So if we take the energy of the hot iron, the Q hot, and we add it to the energy of the cold water, Q cold, that's going to equal 0. All right? That's what it means to have a conservation of energy. You're not making or destroying any energy. Now, each of those Q's is going to have their own MC delta T. So the iron is the hot part. So you can see there I put M iron, C Fe iron, delta T iron. And then the cold will do the same thing, but for the liquid water. M times the water times C of water times delta T of water. So in this problem, all right, we're going to plug and chug. Delta T is final temperature minus initial temperature. And the goal here is just to find that final temperature. And the final temperature is going to show up 2 different places. We'll see on the next slide. Now, you are going to need some heat capacity values. The iron's heat capacity, 0.449 joules per gram Kelvin. Water, like I said earlier, a very important number that I do encourage you to memorize, 4.184 joules per gram Kelvin. And again, that final temperature is going to be the same for both iron and water. So in both of the delta T's, the delta T for the Fe and the delta T for the water, those are both final minus initial. The initial temperature of the iron is this number, 77.8. The initial temperature of the water, 18.8. But the final temperature, which is going to show up in both of those, that's going to be the same number. Let's just break this down. Each of those MC delta T's, we're going to throw in the different values. So here's the mass of the iron, the heat capacity of the iron, delta T, final temperature minus 77.8. Then MC delta T for water. Here's the mass of water, the heat capacity of water, initial temperature 18.8, and the final temperature, again, same as the other one for iron. And all of that equals 0. Now, this is an equation with only one unknown. So what we want to do is get all the terms for TF on one side of the equals, and then all of the numbers on the other side. And from there, we can solve for TF. And remember, our final answer should be larger than 18.8, but less than 77.8. Hot and cold makes warm. So if you distribute this out, and I encourage you to do it, okay, 88.5 times 0.449 is about 39.7. And you want to multiply that by both TF and negative 77.8. So you get 39.7 TF minus 3090. 244 times 4.184 is 1020. Multiply that by TF and that number by negative 18.8. 18.8, and you get these terms. So what you want to do is combine the TF terms together. That's 1060 TF, and then add 3090 and add 19,200 to both sides, so you get the numbers on the other side. Once you have 1060 TF equals 22,300, you can divide both sides by 1060. You'll get TF by itself, and on the other side, 22,300, divided by 1060, that comes out to be 21.0 degrees Celsius. And notice how the final temperature is between 18.8 and 77.8, so that's good. Now, most of the time, the final temperature will be closer to the temperature of the water. Water has a higher heat capacity, which makes it the final temperature closer to it. In this problem, we also had a lot more mass of water too. So for all of those reasons, the temperature is closer to the water than it is the iron.